This movie deals with density. It is intended for viewing before students do a laboratory experiment designed to illustrate the application of Archimedes' principle in determining densities of solids and liquids. Upon completion of the laboratory activity associated with this movie, students will be expected to be able to define and differentiate density and specific gravity, define buoyancy and state Archimedes' principle, and determine the density of solids and liquids. Density is defined as mass per unit volume. To calculate the density of an object, we simply take its mass and divide it by its volume. Here are some examples illustrating the application of this simple concept. The density of an object depends on what it is made of. So, density can be used to help in identification. Suppose a 10-gram sample of liquid occupies a volume of 10 milliliters. Could it be water? To answer this question, we calculate the density of the liquid by dividing the mass, which is 10 grams, by the volume, which is 10 milliliters. The density of the liquid is 1 gram per milliliter. By definition, a milliliter is exactly 1 cubic centimeter. So we can also say that the density of the liquid is 1 gram per cubic centimeter. In SI units, the density is 1,000 kilograms per cubic meter. So, could this be water? If we were to look up the density of water, we will find that it is, in fact, 1 gram per mil. But water may not be the only liquid that could have a density of 1 gram per mil. So the answer is maybe. If we came up with a density that is significantly different from 1 gram per mil, say 1.2 grams per mil, then we could say that it's not water, at least not pure water. We rearranged the defining equation for density to solve for the volume, V, in terms of the density and mass, M. A practical application of this in chemistry involves measurements of chemicals. It's not always convenient to weigh liquids. They could be corrosive and ruin an expensive balance if spilled. Suppose you want 5 grams of ethyl alcohol for an experiment. What volume would you dispense if you prefer not to use the balance? We need to look up the density of ethyl alcohol. If we do, we will find that the density is 0.79 grams per mil. Dividing 5 grams by 0.79 grams per mil gives us 6.3 milliliters. Thus we could take out a small graduated cylinder, fill it to the 6.3 mil mark with ethyl alcohol. This should give us 5 grams of ethyl alcohol. The specific gravity of an object is defined as the ratio of its density to that of a reference sample. For liquids, the reference is water. Note that specific gravity is unitless since it is a ratio of two things with the same unit. What is the specific gravity of ethyl alcohol if its density is 0.79 grams per cubic centimeter? Since the density of water is very close to 1 gram per centimeter cubed, the specific gravity is essentially equal numerically to the density in gram per centimeter cubed. In other words, the specific gravity of ethyl alcohol is 0.79. No units. Experimental determination of density can be very straightforward. We determine the mass, determine the volume, then divide the mass by the volume. By now you should be familiar with ways of determining the mass. Two of the commonly used instruments are the triple beam balance and the electronic balance. The triple beam balance is shown here on the left. To use a triple beam balance, you must first level the beam with nothing on the pan and all riders at the 0 marks on the beams. Put the object to be weighed on the pan, then move the riders to rebalance the beams. Modern laboratories generally have electronic balances with a digital readout, such as the one shown on the right. The typical procedure for using an electronic balance is as follows. Press the tare or 0 button. This makes the digital display read 0. Then you simply place the object to be weighed on the pan and the digital readout will display the mass. The mass shown automatically excludes the mass of anything that was on the pan when the tare button was pressed. The most commonly used instruments for precise measurements of volumes of liquids are graduated cylinders, burettes, and pipettes. Burettes and pipettes are more precise than graduated cylinders and are commonly encountered in chemistry laboratories. The tip of a burette is essentially a tap. By turning the stopcock at the bottom, liquid is dispensed from the burette. The scale on the right shows the typical markings on a burette. To calculate the volume of liquid dispensed, you would need to take the difference in the liquid levels before and after the liquid was dispensed. You will find that water typically forms a curved surface called a meniscus. For consistency, readings of water levels should be made at the bottom of the meniscus at eye level. A pipette works like a drinking straw. You put liquid up the pipette with a rubber bulb or pump. Then dispense a desired amount of liquid by allowing it to drain into some container. A final very important note about measuring liquid volumes. Beakers are never used for precise measurements of liquid volumes. The volume marks on beakers are neither accurate nor precise. They are only approximations. Beakers are intended to temporarily hold liquids. They are designed so that liquids can be easily poured into another container. To determine the volume of a solid, we can measure its dimensions if it has a regular shape. For example, the volume of a rectangular block is just equal to its length times its width times its height. A cylinder has a circular cross-section, which is constant. The volume of a cylinder is simply the area of the cross-section, pi r squared, multiplied by the height or the length, h. In the formulas given here, r is the radius of the cross-sectional area. D is the diameter, which is twice the radius. For a sphere, the volume is equal to 4/3 pi r cubed, where r is the radius of the sphere. The diameter of the sphere is twice the radius. In terms of the diameter, d, the volume of a sphere is pi d cubed over 6. Obviously, most objects do not have one of these regular shapes. A commonly used method for determining volume is water displacement, as illustrated here. The object is dropped into a graduated cylinder containing water. The change in the water level is equal to the volume of the object. What would you do if the object doesn't sink in the water, like a cork, or if the object dissolves or reacts with water? If the object doesn't sink, you can try pushing it in with a long thin needle, or you can try a different liquid. If the object dissolves or reacts with water, you can also try a different liquid. Archimedes' principle states that an object in a fluid experiences an upward force equal to the weight of the fluid that it displaced. This upward force is called the buoyant force. Consider the cylinder submerged in water as shown in the picture here. Suppose the cylinder has a volume of 50 cubic centimeters. What is the buoyant force on the object? The buoyant force is equal to the weight of water displaced by the cylinder. The volume of water displaced is equal to the volume of the cylinder. It's 50 cubic centimeters. The mass of the displaced water is equal to the density of water times the volume of the displaced water. The density of the water is 1 gram per cubic centimeter, so the mass of the displaced water is 50 grams. We multiplied this by the acceleration due to gravity to get 0.49 newtons. The water exerts an upward force of 0.49 newtons on the cylinder. This counteracts the force of gravity, which is equal to the weight of the cylinder. The cylinder, then, will apparently weigh less than the water. Let's see if we can come up with a general formula for buoyant force. It's equal to the weight of the liquid displaced, which is equal to the mass times the acceleration due to gravity. The mass of the liquid volume is equal to the volume of the liquid displaced, which is also the volume of the solid, times the density of the liquid. You will note that the buoyant force depends on the density of the liquid and the volume of the object. The more dense a liquid, the stronger the buoyant force. That's one reason it is harder to sink in the Dead Sea, which is unusually dense due to a high concentration of dissolved salts. The buoyant force depends on the volume of the object, not on what it is or what material it is made of. However, the mass of an object does factor into whether it will sink or not. If its weight exceeds the buoyant force, then it will sink. Otherwise, it will float. In other words, whether the object will sink or not depends on its weight, which is proportional to its mass, and the buoyant force, which depends on its volume. The weight pulls down on the object while the buoyant force pushes up. In fact, it's the density of the object, the ratio of its mass to its volume, which will determine whether it sinks or floats in a given liquid. We could use this fact to devise a procedure for determining the density. The apparent weight of a solid in a liquid, shown here as W prime, is given by the downward force of gravity, mg, minus the upward force due to buoyance, which is equal to the volume of the object times the density of the liquid, times the acceleration due to gravity. Let's define m prime as the apparent mass of the solid when it's in the liquid. W prime equals m prime times g, and replace the volume of the solid, V, by m over d sub s, where d sub s is the density of the solid and m is the actual mass. We can derive an equation relating the density of the solid to the density of the liquid, and the actual and apparent mass of the solid. The density of the solid is equal to its actual mass times the density of the liquid, divided by the difference between the actual mass and the apparent mass. In other words, if we weigh a solid while immersed in a liquid, we can determine its density, as in the example shown here. Suppose a 50-gram solid has an apparent mass of only 40 grams in water. What is the density of the solid? We simply plug the numbers into the appropriate formula. The actual mass, m, is 50 grams. The density of water is 1 gram per cubic centimeter, and the difference between the actual and apparent masses is 10 grams. This gives us a density of 5 grams per cubic centimeter for the solid. An important note before we proceed. Archimedes' principle applies not only to liquids but also to gases. Liquids and gases are collectively referred to as fluids. Air does exert a buoyant force on objects, but we will ignore it in this lesson since it is negligible for our purposes. It is negligible because the density of air is very small compared to liquids. In other words, we will assume that the actual mass of an object is equal to the mass obtained by weighing it in air. We will not go through the trouble of weighing the object in vacuum. Another important note. The equation we have here can also be used to determine the density of an unknown liquid. If we know the density and actual mass of a solid, and measure its apparent mass in an unknown liquid, then we can calculate the density of the liquid, d sub L. We have seen that if a solid is immersed in a liquid, say liquid X, then the density of the solid is equal to the actual mass of the solid, m, times the density of the liquid, d sub X, divided by the difference between the actual mass of the solid and its apparent mass while immersed in liquid X, m sub X prime. If we immerse the same solid in another liquid, say liquid Y, we get a similar formula. The only difference is that we use the density of liquid Y, d sub Y, and the apparent mass of the solid while immersed in liquid Y, m sub Y prime. The right-hand side of these two equations are obviously equal to each other. They are both equal to d sub S. From this equality, we can easily show that the ratio of the density of X to the density of Y is equal to the ratio of the differences in the apparent mass to the actual mass in the liquids. If we know the density of one of these two liquids, then we should be able to calculate the density of the other from measurements of apparent masses. If we use water for liquid Y, the ratio we get is the specific gravity of liquid X. Here's an example. Suppose a 50-gram solid has an apparent mass of only 40 grams in water, but in liquid X, its apparent mass is 42 grams. Calculate the specific gravity of liquid X. The specific gravity of liquid X is the ratio of its density to that of water. This ratio is equal to the ratio of the differences between the actual masses, 50 grams, and the apparent masses when the solid is immersed in the liquids. In liquid X, the difference is 50 minus 42, or 8 grams. In water, the difference is 50 minus 40, or 10 grams. The ratio of 8 to 10 is 0.8. Therefore, the specific gravity of liquid X is 0.8. Let's see if this answer makes sense. Liquid X is less dense than water. Therefore, compared to water, liquid X will exert a lesser buoyant force on the same object. Thus, the object is apparently heavier in liquid X than in water. The apparent mass in liquid X is 42 grams versus 40 grams in water. So far we have discussed the determination of density by completely immersing the solid in a liquid. This is fine for solids that are more dense than the liquid. For solids that are more dense than the liquid, the buoyant force would be less than the force of gravity on the solid, and the solid will sink. If the solid is less dense than the liquid, it will float. What then? Archimedes' principle still applies to the part of the solid that is submerged. We also know that the net force on the floating solid is zero. That is, the upward buoyant force is equal to the downward force of gravity, which is the weight of the solid. Let's see if we can derive how much of the solid will be submerged in this case. Let M and V be the mass and volume of the solid. The weight of the solid is mass times acceleration of gravity, mg. Let F be the fraction of the solid volume that is submerged. For example, if only 40% of the solid is submerged, F is 0.4. Then, the actual solid volume that is submerged is F times V. This is also the volume of the liquid displaced by the solid. The mass of the liquid displaced is equal to the volume displaced, F times V, multiplied by the density of the liquid, d sub L. We multiply this by G to get the weight of the solid displaced. According to Archimedes, this is the buoyant force. Therefore, the buoyant force, F times V, times d sub L times G is equal to the weight of the solid, M times G. Solving for F, we get that F is equal to d sub S divided by d sub L. In other words, the fraction of the solid volume that is submerged is simply the ratio of the density of the solid to the density of the liquid. Note that this ratio is less than 1 since the solid is less dense compared to the liquid. If the solid is more dense than the liquid, then the buoyant force will not be able to exceed the force of gravity, and the solid will sink to the bottom. We have seen that if the density of a solid is less than that of a liquid, then the solid will float if we put it in the liquid. Furthermore, the fraction of the solid's volume that is submerged is equal to the ratio of the densities of the solid to that of the liquid. Suppose a cylindrical cup, represented here in red, floats on water such that half the height of the cup is submerged. What is the density of the cup? Since half the cup is submerged, the ratio of densities is 1/2. The density of the cup over the density of water equals 1/2. Since the density of water is 1 gram per cubic centimeter, the density of the cup is 0.5 grams per cubic centimeter. If the cup were placed in ethyl alcohol, it will also float. Its density is 0.5 grams per cubic centimeter, which is less than that of alcohol, given here as 0.79 grams per cubic centimeter. The ratio of densities is 0.63. This means that 63% of the cup will be submerged in alcohol. Does this make sense? The cup sinks deeper in alcohol than it does in water. We expect this since alcohol is less dense than water. For it to exert the same amount of buoyant force as water, a bigger volume must be displaced. More of the cup submerges. A hydrometer is a convenient instrument to use for measuring densities of liquids. It is essentially a long tube that is weighted at the bottom. To use a hydrometer, simply put it in the liquid. The specific gravity of the liquid corresponds to the mark at the liquid surface. If you examine the hydrometer scale on the right, you will note that the numbers decrease going up. The farther the hydrometer sinks, the less dense the liquid. If you were to design your own hydrometer, you can calibrate it by putting it in water. Mark off the water level and label it as 1.0. Here's an overview of the experiment you will be doing in lab. In the first part, you will determine the density of a metal cylinder by directly measuring its mass and volume. Use the balance to determine the mass. Use two different methods to determine the volume of the cylinder. For one method, use a vernier caliper to determine the dimensions of the cylinder. Use water displacement for the other method. That is, sink the cylinder in a graduated cylinder with water. In the second part of the experiment, you will determine the density of the metal cylinder from the difference in its actual mass and its apparent mass in water as shown in the pictures here. We will take the mass in air as the actual mass. That is, we will ignore the buoyancy of air. Suspend a meter stick at its center of gravity. Hang the cylinder on the left side 40 centimeters away from the pivot point. Then hang counterweights on the other side to balance the stick. Hang the counterweights 40 centimeters away from the pivot point to simplify the calculations. You will recall that the second condition for equilibrium requires that the sum of the clockwise and counterclockwise torques be equal when the stick is balanced. Torque on the left side is equal to the weight on the left arm of the stick, which is equal to the total mass, m sub L, hanging from the left arm, times the acceleration due to gravity, g, times the moment arm of this force, s sub L. Similarly, the torque on the right is the weight on the right arm, which is equal to the total mass, m sub r, hanging from the right arm, times the acceleration due to gravity, g, times the moment arm of this force, s sub r. Note that it cancels out. Since we set the pivot point at the center of gravity of the stick and hung the weights at equal distances from the pivot point, s sub L equals s sub r. Therefore, the mass of the left arm must be equal to the mass on the right arm when the stick is balanced. Actually, we need to refer to the total mass on the left arm as the apparent total mass. In this case, where the cylinder is immersed in water, since it is equal to the mass or apparent mass of the cylinder plus the mass of the lever clamp, we will ignore the mass of the strings. In your calculations, make sure that you include the mass of the hanger and lever clamp when you calculate m sub r. Subtracting the mass of the lever clamp on the left arm from the m sub r gives us the mass or apparent mass of the cylinder. In part 3 of the experiment, you will determine the specific gravity of an unknown liquid by determining the apparent mass of the cylinder you used in part 2 when it is immersed in an unknown liquid. The ratio of the density of unknown liquid to the density of water is equal to the ratio of the differences in the actual mass of the cylinder and the apparent mass in the two liquids. In the equation shown here, m minus m sub x prime is the difference between the actual mass and the apparent mass in the unknown liquid. M minus m sub w prime is the difference between the actual mass and the apparent mass in water. Finally, we will determine the specific gravity of water in an unknown liquid using a hydrometer as shown in the picture.